In this video, we're going to use the concepts about freefall and the equations for one-dimensional motion to analyze the problem where a flower pot is falling from a windowsill 25 meters above the sidewalk. We'll start out writing out what we are given. First of all, we see the number 25, so that tells me that the displacement is going to be 25 meters. When we're given a number like that, like displacement, which we know is a vector, we need to ask ourselves about its direction. This problem says that the flower pot is falling. That means it's going downward. Therefore, this displacement is negative. It says that it falls from a windowsill. Well, usually when something falls, it starts at rest. And so the initial velocity is 0. Anytime you're doing a free fall problem, we always know the acceleration. That's the acceleration due to gravity, or gravitational acceleration. And from your textbook, you should know that that is equal to negative 9.8 meters per second squared. Now, your textbook may use negative 9.81 meters per second squared, being a little bit more precise. We'll stick with negative 9.8. It varies a little bit depending on your location. Looking at all of my givens, the units match, so I'm able to go and move on to the step where I'm looking for the unknown. A says, how fast is the flower pot moving when it strikes the ground? So V final is what I'm looking for in part A. Now, you may be tempted to automatically say that it's going 0 meters per second. It hits the ground and stops, after all. But in physics, when we ask that question, how fast is it moving when it strikes the ground, we're really asking how fast is it moving the split second before it strikes the ground. So that's actually a number above 0. It's a value that's not signifying that it is stopped. Okay, so looking at the 4 values that I have written up on the board here, the variable I'm missing is time. So I'm going to pick one of the 4 equations that doesn't include time. That equation is V final squared equals V initial squared plus 2a delta x. Looking at this equation, I know that V initial is 0, and so I'm going to cross that out using an arrow and a 0 at the end of the arrow. That means I can kind of ignore that term as I'm going about my way. So V final squared equals 2a delta x, and then we take the square root of both sides. So V final is equal to the square root of 2 times negative 9.8 meters per second squared times negative 25 meters. Now, one thing to point out, it's not uncommon for people to forget that negative sign in front of the 25. But if I had forgotten that negative sign in front of the 25, I'd end up with a negative under my radical. We know that's not possible. Math class tells us that. We get imaginary numbers that way. Please do not just ignore the negative under the radical if that happens to you. That's an indication that you've done something wrong. Go back and look through what you plugged in and make sure you didn't miss a negative anywhere. For this problem, the answer is 22.1 meters per second. Now, because the problem says how fast was it moving, I don't need a direction with that. 22.1 meters per second is a pretty reasonable speed for it to be falling. If it went 25 meters is like 2.5 times the length of this classroom. So that's our answer to part A. Moving on to part B. How much time does a passerby on the sidewalk below have to move out of the way before the flower pot hits the ground? This is a fancy way of asking how much time does it take for the flower pot to hit the ground. So in part B, we're looking for time. We have all of our other variables in this case, so I'm going to pick the easiest equation. And in my opinion, that first equation, V final equals V initial plus acceleration times time, is the easiest one. Again, V initial is 0. I don't need to worry about it at all. So I have v final equals acceleration times time. And if I divide both sides by acceleration, I get that time is final velocity divided by acceleration. And final velocity, we said, was 22.1 meters per second. And acceleration is negative 9.8 meters per second squared. If I plug those numbers into my calculator, I get negative 2.26 seconds. But there's something wrong here. I'm not allowed to have negative time. That doesn't make sense. Again, an indication that I've done something wrong. I've missed a negative sign somewhere. And that negative sign I missed is on the final velocity. When I solved for it up ahead here, up above, I used a square root symbol. From math class, we know that there's supposed to be a plus or minus in front of the square root. In physics class, we have to ask ourselves, which one of those two, plus or minus, makes sense? This flower pot was falling downward. That tells me that its velocity should be negative. And therefore, when I do negative 22.1 divided by negative 9.8, I end up with a positive 2.26 seconds. Again, a reasonable amount of time for it to fall. Let's move on and try another problem. This problem, number 36 in your textbook, talks about two students being on a balcony. One student throws a ball downward, and the other one throws a ball upward. There are many things that we're solving for here. But let's start not worrying about what we're solving for. Let's start by writing out what we're given. So there's two balls in this case instead of one object. And so I'll call them A and B, just like I commonly do. And I'll write out the givens for each. First of all, it says that two students are on a balcony 19.6 meters above the street. I'm going to be looking at from the point where they start to the point where they hit the ground. And so both balls will have the same displacement. And again, the displacement is downward, so it's negative. Negative 19.6 meters. It says that one of them is thrown vertically downward. That gives me my initial velocity of negative 14.7 meters per second. Again, I use a negative sign to indicate down because I can't plug a downward arrow or the word down into my calculator. And it says the other ball is thrown up at that same speed. So that one's positive because we think of upward as being positive. Another piece of information, because both balls are in free fall, is that acceleration is negative 9.8 meters per second squared. All of my units match, so I don't have to do any conversion. I can move on to the questions. Part A, what is the difference in time the balls spend in the air? So for part A, I'm looking for time. And really I'm looking for the time of A minus the time of B. Or maybe vice versa. I want to get my difference in time to be positive. So we'll take the larger number minus the smaller number. Okay, well, to do that, I have to find the time for each of them. Looking at the information I'm given, the thing that I'm missing is the final velocity. So, if I look at the equation that doesn't have final velocity says delta x equals v initial t plus 1/2 at squared. Okay, I'm going to pause here for a second. To be able to solve for time in this equation, because this is a quadratic equation, I'd have to use the quadratic formula. Now, if you're comfortable using the quadratic formula, by all means go ahead and use it. But if you really would like to avoid using the quadratic formula, there's another way. The other way instead of using this equation, would be to first solve for the final velocity so that we have another piece of information. I'm going to choose the equation that doesn't have time in it since I don't know time, which is this equation here. Final velocity in this equation is the square root of the initial velocity squared plus 2 times acceleration times displacement. I'm going to do that for both parts A and B, or for both balls A and B. And the only difference is the sign of that initial velocity. So 14.7 meters per second squared plus 2 times negative 9.8 meters per second squared. I'm running out of room here, so I'll scoot this over. Times the displacement, which is negative 19.6 meters. When I plug this into my calculator, I get 24.5 meters per second. Now, I use the positive initial velocity in that case. But ball A has a negative initial velocity because it says it was thrown downward. Well, really, it doesn't matter, because if I put a negative sign in this equation, that negative sign gets squared, so it goes away. So this is the final velocity for both balls A and B. Now remember, in the last problem, I said that in math class we put a plus or minus out front of the radical. In physics class, we have to decide that direction. Right before it hits the ground, is it moving up or down? Hopefully you answered down. So that means that this final velocity should be negative. Now that we have the final velocity, we can much more easily calculate time using the equation v final equals v initial plus acceleration times time. Now there's other equations you could use. I just think this one's the easiest. To solve for time, the first thing I would do is subtract v initial from both sides. Then I would divide both sides by acceleration. So I get that time is v final minus v initial divided by a. Here's where parts A and B are going to be different. For A, my initial velocity was negative. So I have minus negative 14.7 meters per second. Still with an acceleration of negative 9.8 meters per second squared. When I plug this into my calculator, I end up getting a time of exactly 1 second. In part B, using the exact same equation, time is negative 24.5 meters per second minus a positive 14.7 meters per second divided by negative 9.8 meters per second squared. This time I get a time of 4 seconds. So to answer part A, the difference in time, really I'm doing the time for ball B minus the time for ball A, so that I get a positive difference in time, and that's 3 seconds. A reasonable answer. Now it seems like we did a lot of work for part A, but the awesome part is that we actually answered part B in the process of answering part A. Good, right? So part B says, what is the velocity of each ball as it strikes the ground? We already know that that is negative 24.5 meters per second. Part C, how far apart are the balls 0.8 seconds after they are thrown? So part C is a little bit different. Part C is asking us to find the change in displacement. I'm going to actually put absolute value around there so I don't end up with a negative number. This time, we're given the time. The time is 0.8 seconds. So we need to solve for the displacement of ball A and solve for the displacement of ball B. And then I'll subtract the two. Well, I know initial velocity. I know final velocity. I know time. I know acceleration. So there are multiple equations that you could use. I'm going to pick the equation that says delta x is 1/2 initial velocity plus final velocity times time. For A, I have 1/2 times negative 14.7 meters per second plus negative 24.5 meters per second multiply that by the time of 0.8 seconds. I end up getting the displacement for ball A to be negative 1.57 meters. For ball B, there's only one small difference. And that one small difference is that instead of a negative 14.7, I have a positive 14.7. When I plug that into my calculator, I end up getting negative 0.39 meters. So I subtract one of these from the other, and I find that the distance between them is 1.18 meters. Again, a reasonable number. So now I want you to take what you've learned in these two videos and try it yourself. This problem talks about a small first aid kit being dropped by a rock climber. The rock climber is descending steadily at 1.3 meters per second. I'm looking for two things. I'm looking for the final velocity of the first aid kit, its velocity after 2.5 seconds, and how far the kit is below the climber. My hint to you is to this problem is to not forget about the fact that even after the climber drops his first aid kit, he is still descending steadily at 1.3 meters per second. Do this problem in your notebook and bring it to class with you the next time we meet.